Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good day. So in this video, we are going to continue with the axiom of real number. So if you recall again, we have three main axiom of real number. So the first one is the field axiom, the second one is the order axiom, and the last part that we are going to do today, or we are going to cover today, is the completeness axiom. So from the completeness axiom, I'm going to introduce you a concept. We call it as supremum, and also related to supremum is the infimum. So from there, we are going to study, or we are going to prove theorem related to the supremum and also infimum. So let us continue. So before we are going to introduce about the completeness axiom, so I need to introduce to you some of the basic properties, or some of the basic concept that we need to know. So let us start the introduction. So first of all, we need to know about the bounded above and also bounded below. So we call that set M is a bounded above if there exists B such that this B is bigger than any M for all M inside the capital M. So such set we call it as a bounded above, and that B is called upper bound. So you can think a way that if you can find a number which is bigger than any number inside the set, then the set M can be called as bounded above. So for example, if you have a set that contain from 1 to 2, and then you can imagine that 3 is bigger than any number inside the set of 1 to 2. So therefore we can say that here therefore we can say that 3 is the upper bound of the set M, and it is bounded. The set M, we call it as a bounded above. So the same thing if we consider bounded below. So let us consider the same example where we take the set M equal to 1 to 2. So here you can see that 1, or we can take 0 as a lower bound. So we can say that here the set M from 0 to 1 is bounded below. So this concept is not that difficult to understand. So you just need to know what is the biggest value. Is there any number that bigger than any value inside the set? Then you already can claim the set is bounded above. The same thing with the bounded below. Okay, so maximum and minimum here. So M is called maximum of M if and only if M is an upper bound and it is inside the set itself. So these are the condition to be maximum. So it has to be one of the upper bounds, and it also need to be inside the set M itself. So you cannot take the maximum value which is outside of the set. So the same thing, or the same situation, if we consider the minimum here. So it has to be one of the lower bound, and also it need to be inside the set. So we can see that here the upper bound and lower bound for a set no need to be unique. So you can have a lot of upper bound and we can have a lot of lower bound. So let us consider this example, right? Completely the upper bound, lower bound, maximum and minimum if exists. So in some case, the set might not have any maximum or minimum. So let us consider the first example here. So the set from 0 to 1. So to write completely the set of upper bound, it is set of contained inside the real number in such a way that is more than 1. and lower bound is set of x inside the real number such that x is less than 0. So any number which is bigger than 1, we can call it as a upper bound for this set, the first set here. And any number which is lesser than 0, we can call it as a lower bound for this set. And as you can guess that here, to be a maximum value, it has to be inside the element itself. So here we have 1 is inside the element here, inside the set here. So therefore we can say that 1 is the maximum value, while the minimum value for this set is 0, because 0 is inside the set. So we record again the definition of maximum and minimum. It has to be one of the upper bound, and it also need to belong to the set itself. So you cannot take the maximum value or minimum value outside of the set. Okay, now let us consider another example in which it doesn't have any maximum and minimum value. For example, here the set of open interval 0 to 1. So the upper bound is from x is bigger than 1, and the lower bound is any value of real number x less than or equal to 0. But the maximum value does not exist because 1 here is not included inside the set. So you cannot take, or we don't have any maximum value. If you say that 0.9 is the maximum value, then I can find another number which is inside the set but is bigger than 0.9, which is 0.99. So therefore the maximum value does not exist. So the same situation or the same argument you can use to say that minimum value does not exist. So the other two example here is going to be your assignment 2. So at the end of the slide, you are going to look the due date of the assignment. So there is several questions that you need to do. So we are going to go through the slide after this. Okay, so this one you need to submit. So next one, after we know already what the meanings of upper bound and lower bound, we are going to introduce with the supremum and also infimum. Okay, so first of all, the definition of supremum is that the least upper bound of a set. So that is called a supremum. So as you recall again, as you remember, I said that the upper bound no need to be unit number. So it can have infinitely many upper bound. So from those upper bound, you are going to take the smallest one or the least one. So that the least upper bound or the smallest upper bound, we call it as a supremum. Why? From the set of lower bound, so you are going to take the highest lower bound, and that highest lower bound is called the infimum. So as you can see, for example, here is the set of M, and this one, okay, sorry, so the blue one is actually representing the set of M, and here you have list of upper bound, the red one and the green one here. And then how you are going to choose the supremum in such a way, you are going to take the least upper bound amongst the least upper bound among the upper bounds here. So all from all the upper bound here, you are going to take the smallest one from them. So that number is going to be called supremum. Okay, so a remark here. So if there exists a maximum value, then that maximum value is actually the supremum. Okay, now let us consider another example. For each of the following sets, find its supremum, maximum, infimum, and also minimum value if they exist. Okay. So for the first one, we have a set of 5, 8, 9, 10, 12. So the maximum is 12, and based on the remarks here, if there exists a maximum, so therefore this maximum must be equal to the supremum. So therefore the supremum must be equal to 12, and the minimum value is 5. So the same reason here, if we have the minimum value, then that minimum value must be equal to the infimum. So that's why we have this answer. So next one is open interval from -3 to close interval 4. So of course 4 here is included in the set, so therefore the maximum value is 4, and based on the remarks that we have previously, the maximum must be equal to the supremum, which is also equal to 4. But in this case, -3 is not included in our set. So therefore, the minimum does not exist. But we can have infimum equal to -3. So this is the difference between the minimum and infimum. It could be, the infimum could be not inside the set, while the maximum and minimum must be inside the set. So the supremum and infimum, you can take a number which is not inside the set. For example, in this there's example number 2 here. Okay, so the example number 3 is a set of 1 over n inside the natural number. So you need to list all the supremum, maximum, infimum, and also minimum if they exist inside this set. Okay. So this is the axiom, the last axiom, which is the most important axiom in a real number. So every non-empty set of M which is bounded above has a supremum, and we denote is alpha. So if you take any bounded set, it always have a supremum value. So you can always take a value, you can always find from a bounded set a supremum value from that set. So this is a completeness axiom. Okay, so now let us consider one theorem here. So every non-empty set M subset of R which is bounded above has infimum. So from the this axiom, you can always ask that why we only have supremum here. Well, how about the infimum? So that infimum is answered in this theorem. So when we have a bounded below, then it also have infimum value. So it is actually coming from the axiom here. So the proof relies on this axiom. That's why in the axiom here we didn't write about the bounded below. So we just write for the bounded above, and as a corollary, so we will get this theorem. So let us prove this theorem. So now let's just consider M is a bounded below set. So now we are define negative M in the following way. So we are going to take negative of each of the element inside the M. So therefore we can therefore negative M is bounded above. So you have a bounded below set, then you take negative of it, so of course it's going to be bounded above set. So by completeness of R, so because this negative M, the set of negative M is bounded above, so based on the last axiom that we learned, we know that there exists supremum of this set negative M. So we are going to write as here. So now we are going to show this negative s is the greatest lower bound for of m. So here we claim that this s is the supremum of negative m, but we are going to show the negative of s here is going to be the greatest lower bound of m. So let us take, as you recall again, the set of lower bound could be infinitely many. So we are going to what we are going to do now, we are going to compare another lower bound with the negative s here. So what I'm going to show is that I'm going to show this negative s is the greatest lower bound amongst the lower bounds. Okay, so now we are going to take t as another lower bound for m. So therefore, because t is the lower bound, so therefore any s must be bigger than t for all s inside the m. So you have to understand this word because we already take t is a lower bound of m. So what do we mean by lower bound of m? So it means that any value inside the x must be bigger than t. So therefore we are going to take the negative of this inequality. So we are going to get negative x less than negative t for every x inside m. So against here, what we can say that this negative t is an upper bound of negative m, right? Because we found that here negative t is bigger than any of negative x. So therefore, it must be an upper bound for negative m. Okay, so the set of negative m. So since s, so we already say that s here is a supremum, right? So therefore, s is the lowest upper bound or the least upper bound for negative m. So you record again here. So we already set negative m like this, and then we say that it is bounded above. So from the bounded above, from the axiom of completeness axiom of R, we say that there exists supremum. So that supremum is the least upper bound of negative m. So from all the upper bound that we have, we are going to take the least upper bound and we write it as s here. So from what we have discussed before, we say that negative t is also upper bound. So recall that s is the least upper bound. So therefore, s must be less than negative t. So that is a key point here that you have to understand. S is the least upper bound. So negative t is also one of the upper bound. So therefore, this inequality for s must be less than negative t. So therefore, when we interchange the negative part here, so we are going to get negative s is bigger than t. So here we already proved that negative s is greater than any t. So t here we claim that t is another lower bound of m, but we we claim that we prove that here negative s is bigger than t here, which is the greatest lower bound amongst the other lower bound. So therefore, we prove that negative s is the greatest lower bound. So therefore, the infimum of f of m must be equal to negative s. So let us continue on the next theorem, approximation properties of supremum and also infimum. So the theorem here say that for every epsilon more than 0 and m subset of R, so m here is a subset of real number, then one has the following statement. So if m has a supremum alpha, then there exists x inside m such that x is bigger than alpha minus epsilon. So what we are going to say that here, whenever you minus alpha, or whenever you minus the supremum with a small number, you already you can find x inside the m such that it has to be bigger than alpha minus epsilon. So meaning to say that here, when you minus a very small number to the supremum, you will be inside the set of M. Okay, I repeat again. So, here, the approximation properties of supremum and infimum here want to say that, so let's say that you have the set of M, and M has a supremum of alpha. So whenever you minus alpha with a small number, then you will be inside the set of M already. Okay, so that's why we have x is bigger than alpha minus epsilon here. So another key point that you have to understand here is that the wording exists here. So this x is not for all x inside M, but it is enough for you just to find some x which satisfy which bigger than alpha minus epsilon. In fact, you don't need to find actually, but we will, from the properties here, it actually exists. So we can find the value or the element of M such that it will satisfy these properties. Okay, so the same thing if we consider the infimum value here. So the infimum part say that if we add the infimum with some positive number, you will be inside the set of M itself. So in other words, we can say that there exists x inside M such that x must be less than alpha plus epsilon here. Okay, so I'm going to prove the first part only. So the second part will be your assignment. Okay, so the proof will be looks like this. So assume that alpha equal to supremum of M. So based on the theorem here, say that if M has supremum, so we can, without the loss of generality, we can assume M there exists supremum of M. Okay, so now by the definition of supremum, so alpha is one of the upper bound. So recall again this the definition of supremum. Supremum, to be a supremum, it has to be one of the upper bound, and from those upper bound we are going to take the smallest one, and the smallest one we call it as supremum. So therefore we have these properties here. So alpha must be one of the upper bound, so therefore alpha must be bigger than x for any x inside the capital M. And then another properties is that alpha must be the least upper bound. So for any number beta less than alpha is not upper bound for A. So here meaning to say that if for any value lesser than alpha here, it cannot be upper bound for M. So now we are given a positive number, epsilon more than 0. So we are going to minus a little bit alpha minus alpha with this epsilon. So when we minus alpha with the epsilon here, so of course it's going to be less than alpha. But this fact say that for any beta less than epsilon is not already upper bound for M. So So this alpha minus epsilon cannot be upper bound for M. So by the properties of number 2. So therefore, there must exist some value of x which is bigger than alpha minus epsilon. So if this not satisfied, then of course there will be some contradiction, because if this is not satisfied, then alpha minus epsilon will be the least upper bound, which is a contradiction because we already say that alpha is the least upper bound. So therefore there must exist some x such that we satisfy x more than alpha minus epsilon. Okay, so the proof for number 2 here is going to be your homework. So you need to write properly to prove this statement. So I'm going to stop the video here. The next video I'm going to continue with the Archimedean properties and some properties of supremum and also infimum. So thank you for watching.